This is part 4 of the tutorial on type classes. In the previous parts, I talked about how to analyze the type signatures of a type class. And in particular, we found that there are algebraic and co-algebraic type classes. Then we looked at type class derivation patterns, and in specific cases, such as free and co-free instance constructors, we ran into the notion of a type class preserving function between two types. Now, at this point, the tutorial goes further into theory than is necessary purely for practical applications. For practical applications, it is sufficient to look at the table that I showed in the first part of the tutorial, where I showed what patterns of type class derivation exist, and I showed how to detect whether the type class is algebraic or co-algebraic, and then I claimed that it follows that all these type class derivation patterns are valid, so they will give you lawful instances of type class from previous lawful instances. So for instance, if you have a co-algebraic type class, then A and B are instances, then then either A, B also will have an instance, and it will be lawful. And similarly for algebraic type classes, will be the pair will be lawful, or a recursive instance will be lawful. And if you know that, it's sufficient to be able to use type classes correctly and write by hand the derivation, or write a library that does the derivation. You don't need to go into proofs and how what is the technique that is necessary for proof. But I would like to do that because I don't think it's written down anywhere in a way that is accessible. Just for my own peace of mind, I would like to know if what I say is true. So I'd like to write down the proof. And the first step toward that is to look at type class preserving functions, which is a useful notion, also motivated by category theory, but a programmer can easily understand what that is without knowing any category theory. And so that's my view also. I'm only looking at this from the programmer's point of view, where I work with certain types and functions and certain properties of those functions that I can write down in terms of code. So as long as I can write it down in terms of code, and as long as it gives me some interesting insights into the code, then this is something a programmer might be interested in learning. So the first step towards that theory is to understand what it means to have a type class preserving function. So let's first consider an algebraic type class and a structure map of this type. P is a covariant functor, as usual. So we might define the type class like this in Haskell, although, of course, as I said, in practice, you would never do it like this. It's inconvenient to have just a big type constructor P here, and every time so it could be a algebraic data type with many variants, and you'll have to put cases everywhere. So it's inconvenient, but it's very convenient to do this for theoretical considerations, for analyzing the general properties. So consider that you have maybe T and U, there are two types that belong to this type class. So a function between T and U, so a function of this type, is called type class preserving if, roughly speaking, the operations on T in the type class are always mapped into the corresponding operations on U. Now this is the intuition. Let me make it quite precise what that means, because the function f doesn't map operations, it maps values of type T into values of type U. What does it mean that it maps the operations? Well, it needs to be formulated quite precisely in terms of values. So here's how. Let's take the monoid type class as an example. So what is the monoid preserving function? the monoid has two operations, mappend and mempty. So we can apply mappend to two values and produce a new value of type t. You can apply f to that value, and then you get a new value of type u. So then what you want is that that value of type u should be equal to using mappend within the type u on the two values ft1 and ft2. So in other words, you start with t1 and t2. You could first combine them in a monoid and then map with f, or you can first map with f and then combine with a monoid in u, and then the results should be the same. So it is in this sense that the function f maps mappend in type t into mappend in type u. Similarly with the operation mempty. So you can take mempty in the monoid t, apply f to that, you get a value of type u, and that should be equal to mempty of type u. So it is in this sense quite literally that f maps operation of type t into the operation of type u. But this is because the mempty has such a simple type. In a more complicated type, you have to substitute arguments and transform the results as well. So let's formulate this property in terms of the functor p alone, rather than talking about operations of specific type classes. So how can we do that? Let's look at the monoid again. Pt has this form. The structure map of a monoid has this type. And the function mappend corresponds to this function f applied to a value of this form, just t1, t2. And then function mempty corresponds to mt applied to the nothing as a value of this type. And the substituted arguments, just ft1, ft2, needs to be substituted like this if you want to look at this value. So that means we need to apply fmap f to this value, where fmap is within the functor p. And that will automatically substitute all the arguments within here. And if you apply fmap f to nothing, it gets again nothing. So we can see that substituting the arguments here and transforming the values corresponds to just using fmap f within the functor p. And that's the beautiful part. So because of this, the condition that f maps operations of t onto operations of u can be formulated just through using fmap f within the functor p. So fmap pertains to the functor p here. And here's how we would then write. So you can take any s of type pt, so any value of this type, say. Then you apply mt to that, transform the result with f. Or we apply fmap f to that and transform the result with mu. And that should be the same. So I encourage you to write it down in more detail to see how that really works. But this is essentially the idea of how to generalize this property, that a function f maps the operations of one type class onto operations of another, or that it or alternatively that it commutes with the operation. And that is how it is written. You can write this in a point-free style like this, and you can illustrate that by a type diagram where I say we begin here. This is an arbitrary value s of type pt. Then I can apply fmap f to that value, I get pu. Then I apply mu, I get a value of type u. Or I can first apply mt to get a value of type t, and then I can apply f. And that should be equal. So starting from any value of type s here, applying these functions and coming here, should give me the same value of type u, no matter in which way I arrive. That, in the language of mathematics, is called a commutative diagram, meaning that you begin with some arbitrary value of this type, you go into all kinds of paths, and when you arrive to the same place, you should be computing the same value as well when you're applying all these functions. So that is the mathematical notation. But this diagram is essentially the same as this equation, except that all the types are written out as well as the functions. In category theory, it is a well-known equation, which is called the p-algebra morphism law. And the function f that satisfies this equation is called a p-algebra morphism. I remind you that a p-algebra is a type T together with a function mt, which is called the structure map of this type, pt to t. So T is a p-algebra, or more verbosely, p-functor algebra, and U is also a p-functor algebra, and the value mt is a structure map of the p-algebra T, and mu is a structure map of U, and then the function f between T and U is a p-algebra morphism. That is the terminology used in category theory. But for us, in the language of types, it just means we have these types, we have these functions implemented in our programming language, and these functions always satisfy this equation. So let's now look at the coalgebraic case. It's a very similar thing. We can just reverse all the arrows, and we had previously pt to t, now we have t to pt. So we just repeat the same diagram with a different direction of arrows. So we, instead of starting here from a value of type pt, we start here from a value of type t. Then we can apply f or apply mt to it, and again we will get to a value of type pu, and we should get to the same value if we are applying first this and then this, or we're applying first this and then this. And that means this equation must hold for all. So this function, which maps a value of type t to a value of type pu, must be equal to this function, which also maps the same types. So this is the p-functor coalgebra morphism law. I did not motivate it because we already motivated the previous one, and you just reverse the arrows, and by formal similarity you write the same kind of thing. But here's an example how it works. So let's look at show. Show is a coalgebraic type class. What is a show preserving function? The structure functor p for show is just a constant functor that returns string. So what is a show preserving function? It's a function that satisfies this equation. If you put here string instead of pu, string instead of pt, this f map becomes identity function. So this is the same value of type string as this one. It means that show, so this is the method show, the show of fx must be equal to show of x. So a show preserving function is a function that transforms the value, but the printed string remains the same. So f preserves the result of applying show. So it maps show from one type to the show of the other. And this is a similar intuition that we had in the algebraic case. So a show preserving function is a function that preserves the methods of the type class. So you can apply the method before this function or after, and you get the same value. So similarly, for the monoid case, you can apply the method before applying f or after applying f, and the result is the same. Let's look at actually even more general case where the type class is neither algebraic nor co-algebraic, and that case is actually only slightly more complicated And we can still formulate type class preserving functions just as easily. The first step is that we gather all methods of the type class into a type constructor, but actually this type constructor won't be covariant or contravariant anymore. And so in order to work with it more conveniently, we use a technique using so-called profunctors. What is a profunctor? Is a type constructor with two type parameters. So for instance, QAB, and it must be contravariant in the first type parameter and covariant in the second. And it is always possible if you write any kind of parametric type expression, then some type parameters will be in a covariant position, others in a contravariant position. And so you can always write down what this Q is for any type expression that you write down. So now the type T here is the same. So because we use just one type parameter, and some of it will be, some occurrences of that type will be in covariant position, others in contravariant. Now a profunctor has a method called diemap, which has this type signature. And this type signature is kind of a generalization of fmap, where the first type parameter is contravariant, so you map A to B and it replaces B to A. And the second type parameter is covariant, so you replace C by D. And this diemap should also satisfy similar laws. So you have an identity. If these are identity functions, then this is also an identity function. And if you have a composition here, then and a composition here, then you get a composition here as well. Similarly to the fmap. So assuming that Q is such a profunctor with diemap which is known, now we deal with this type class. So suppose T and U belong to this type class. Now the structure map now is no longer necessarily just a function, it's something, it's some value of this type. It doesn't have to be a function necessarily. It could be complicated. Suppose that we have T and U belonging to this type class and a function f between T and U. So that function is type class preserving if the following equation holds for the instance values mt and mu. And this condition is called the wedge condition. Now this is an equation that is like this. And this equation is illustrated in this type diagram. So you begin with two values. So this type diagram does not look like a square. It looks like a wedge. So it's called the wedge condition, the wedge condition. So it begins with two values. And this value is mt of this type and mu of this type. And then you apply diemap with identity and f. So that only maps the second type parameter. And here you apply diemap of f and identity, only mapping the first type parameter. And so the result is a value of type q, t, u, and that must be the same value. So that is this equation. So this is a direct generalization of the equation that we had above. So if you rewrite, it takes some work, I'm not going to do it, but it's a mechanical kind of work. If you rewrite this as a qtt, so qxy would be x to py. Then you need to derive what diemap is for that, and then you substitute in here, and you get exactly the same equation as this. As an example of using this technique, let's take the equality type class, which, as we know, is neither algebraic nor co-algebraic. Methods of this type class is just the one method. So this is the profunctor, because you see both of these are in the contravariant position. So they are, let's call this A, and B is just not used in this type constructor. That's okay. Doesn't have to be always both used. the die map looks like this. We just map the arguments, and the function g is actually not used in the die map. If you substitute into the wedge condition for a function f, that is going to be this condition. So in other words, the function f must preserve the result of applying the equal method. So if x is equal to y, then also fx is equal to fy. And if fx is not equal to y, then also fx is not equal to fy. So that is the wedge condition. Indeed, so this agrees with our intuition of what it means that the function f preserves the methods of the type class, or preserves the structure of the type class. So it preserves the methods. It maps one equal method to another. You can say it in that way. So that kind of confirms our intuition of why this condition is what we want. And I will conclude this consideration by an interesting fact that actually type class preserving functions have properties that are known in category theory as the category laws, laws of morphisms, more specifically. So in other words, identity functions are always type class preserving, and that can be seen because of the identity law of die map. If you have identity function f, then t and u are the same type. This is going to be an identity function, this is going to be an identity function, and this is trivially satisfied. It's the same value here. Identity functions map it to the same value. And more interestingly, if f and u, if t and u are two types, and you have a type class preserving function f, and also u and v are two types with a type class preserving function g, then so is the composition of f and g is also type class preserving. So type class preservation is holding for the composition of the two type class preserving functions. Now this is intuitively what we expect, because if one function preserves and the other function preserves, and you can apply one function after the other, you still preserve what you wanted to preserve. But this is intuition, right? So we need to prove this formally, and here's how I prove it. First I draw the diagram to clarify the types. So actually, the assumptions are that this is type class preserving, so this is the wedge condition, which is this wedge. And then the other one is type class preserving, and it is this wedge condition. This, and this. So these two are given. But we need to have this kind of thing. Die map of GF needs to be applied, and we need to have this kind of wedge, which I drew here on the left. How can I derive that this wedge holds? Well, I derive it by computing this diagram to another value of type QTV, and it just so happens that here I have the right kind of functions, so that this square here commutes. Now this is not really easy to see, and I was getting a bit confused, as I always get when I work with commutative diagrams. So instead of drawing a diagram and looking at it for a while, trying to convince myself that it's a correct diagram, which is not easy, I prefer to write down equations, which actually is the same kind of thing. The commutative diagram is just a representation of a certain number of equations. And sometimes it is easier, in my experience, in most cases, it is easier to write down equations and look at the transformations. And so the equation we need to prove is this one. So here is the proof using equations. We have assumptions that these three values are given of types QTT, QUU, and QVV. And these two equations are holding. So these are the equations showing that f is type class preserving and g is type class preserving. And we need to show that the composition gf is type class preserving. And this is the equation that we need to show. So let's look at the left-hand side of this equation. The composition law of die map allows us to decompose this into die map of G applied to die map of F applied to MT. Now this, I underlined it in green, this is the left-hand side here, which we can replace by the right-hand side here by assumption. So let's replace it. And now we again use the composition law of die map. We compose identity with F, we compose G with identity, and we get this. And when we take the right-hand side as the initial point, we do a similar kind of transformation, and we again get, so now we use this. This is the right-hand side here. We replace it by the left-hand side here, which is the assumption. And then we use the die map composition law, and we get the expression which is exactly the same as here. So then we have proved that the left-hand side is equal to the right-hand side. So this kind of proof is much more mechanical. You can go step by step and verify each step, whereas looking at this diagram is kind of not so easy. And it's not mechanical, it's not clear what you begin with, and the arrows going in all directions. So I prefer actually in my book proofs that go line by line with equations. I do always draw a diagram, of course. The diagram helps to visualize how the types are transformed by each of these equations. So in these equations, just like in Haskell code, we don't write types anymore. The types have been checked, so to speak, in the diagram, but then we check the actual computation. So we separate the type checking, which is done by drawing the type diagram, and the actual value checking, which is done by line derivation. And this is what I do in the entire book, The Science of Functional Programming. Line by line derivations accompanied by commutative diagrams, and they play different roles. So the commutative diagrams play the role of a type checker for my equations, and then I use the value, so to speak, value checker. So this concludes this part of the tutorial, and after working with type class preserving functions, we will be ready to look at the type class laws and how the type class laws are represented.